Welcome. In this video, we are going to solve some simple problems on fluid dynamics. This is the first problem. Blood output from the human cardiac is about 5 into 10 raised to minus 3 meter cube, and the radius of aorta through which the blood flow is 10 raised to minus 2 meter. So we are given how much volume of the blood flow across any cross section of the aorta, and it is this much, 5 into 10 raised to minus 3, and the radius of aorta is 10 raised to minus 2. We have to calculate the velocity of blood flow. So first of all, what is the difference between the velocity of fluid flow and the volume rate of flow? In volume rate of flow, we express how much volume of the fluid flow across any cross section. For example, we have a tube here, and suppose the volume of the liquid between these two cross section, each of which have the area A, the liquid in between these two cross section, and suppose the length of this section is L. As the fluid flow, this much section of the fluid will completely flow out of the tube, and it will take certain time. Say the time taken is T. The volume of this section of the fluid is V, and we can see that it has a cylindrical shape. So volume is equal to the base area multiplied by the height. The height in the present case is L. This volume of the fluid flows in time T. So we divide both sides by time. On the left hand side, we get volume flown in time T. This is the volume rate of flow. Volume rate of flow on the left hand side, and on the right hand side we have area multiplied by L by T. I have deliberately written L and T aside from the area A because when this much section of the fluid has completely flown, it has traveled the distance of L. So after this has completely flown out of the tube, it will be in this position after the time T. So we see that it has traveled the distance L equal to its own length. So L is the distance and T is the time taken. So this gives us the flow speed of the fluid. So we write it as AV. So we get the relationship between volume rate of flow and the speed of flow. Volume rate of flow equal area of cross section through which it flow and the velocity of flow. So here is the formula. Using this formula, given volume rate of flow and the area of cross section, we can find the flow speed. Area of cross section can be written as pi r square, where r is the radius of the circular cross section and the radius is given to us. Then we rearrange it. We divide both sides of this equation by pi r square and then obtain this second equation. We simply now substitute for volume rate, the radius, and calculate the answer. The velocity of flow is now 15.9 meter per minute. The unit of time is minute because we have used minute for the unit of time. We can convert meter per minute into centimeter per second. For that, we first convert meter into second. Meter into centimeter. We multiply by 100 and get converted from meter to centimeter. We convert from per minute to per second by dividing by 60 because every minute is a 60 second. So we divide by 60 and get the velocity in centimeter per second. So finally we have velocity equal to 26.5 centimeter per second. Second problem, a square plate of area 100 centimeter square rests on a layer of oil 2 millimeter thick whose coefficient of viscosity is given. Calculate the horizontal force required to impart the plate the speed of 3 centimeter per second. We draw the diagram. This is the layer of oil which is 2 millimeter thick and a square plate rests upon this layer of oil, a square plate. When we pull this square plate, there is a resistance due to the friction between the plate and the layer of the liquid below it, and because of that friction it is difficult to pull this plate easily. So the force of resistance or the force of resistance arises because of the viscous nature of the liquid. When we pull the plate above, the upper layer of the liquid begins to move, and because of the motion of relative motion of the layers of liquid, we have noted that there is a force for there are the forces of friction between the different layers of the liquid, and that force of friction gives rise to the viscosity of the fluid. This problem is based upon a simple formula that gives us the viscous force. The formula for the viscous force is this. We have to move the plate with a constant speed of 3 centimeter per second. So to move the plate with this constant speed, the applied force must be equal to resisting viscous force. So this is the applied force which we must use to move the plate with a fixed speed of 3 centimeter per second. So this is the Newton's law of viscosity. We are given the area of the plate to be 100 centimeters square. The distance between the top and bottom layer of the liquid is dx, which is 2 millimeter. The bottom layer is fixed and only upper layer moves because the plate above it is also moving. So as the plate is moving with 3 centimeter per second, the upper layer of the liquid is also moving with the same speed. So we have the bottom layer fixed and the upper layer moving with the speed of 3 centimeter per second. So there is a change of velocity of 3 centimeter per second between the two layers, and this change of velocity is over the distance of 0.2 centimeter between the layer. So all the quantities required for calculating the force using viscosity formula are known. So we directly pick up this formula and substitute for the viscosity, area, and the change of velocity and the distance between the layer, and finally get the force as 1260 dyne. We note that all the quantities are expressed in CGS unit, centimeter per second. So final answer will also be in a CGS unit. The force will be in dynes. Next problem. A pipe of varying diameter has a diameter of 4 centimeter at one end A and 2 centimeter at the other end B. The velocity of liquid at end A is given. We have to calculate the quantity of flow in the pipe and the velocity at B. So pipe is wider at one end and narrower at the other. We have a 4 centimeter diameter at end A and 2 centimeter diameter at end B, and the liquid is flowing through it. The flow speed at end A, which we denote by V1, it is 70 centimeter per second. The flow speed at end B is not given, that we have to calculate. The diameter is given. So we first find the quantity of flow. The volume flow rate must be same everywhere in the pipe, because whatever fluid enter into a certain region of pipe, the same amount of fluid must leave that region in the same time. Otherwise there will be accumulation of liquid or the depletion of liquid. Because the fluid is flowing steadily, whatever liquid enters, the same amount of liquid must leave. So whatever liquid enter from this region A, the same amount of liquid must leave from the region B in a given time. So volume rate of flow must be same everywhere. So volume rate of flow is given by volume area of cross section multiplied by the velocity of flow. So volume rate of flow at region A, it will be A1 V1, and at region B it will be A2 V2. But the volume rate of flow is same everywhere, so we can either use A1 V1 or A2 V2. V2 is not known, but A1 and V1 are both known, so we use this expression for volume rate of flow. So we simply substitute for area A1 at end A. The area is circular, so we express it in terms of diameter, pi d1 square by 4, then the velocity v1. So diameter is known, velocity is known, we substitute them, and finally volume rate of flow is 880 centimeter cube per second. The unit of time is second, the unit of length is centimeter. Everywhere we must take care what units for different quantities are taken. Now we find velocity of flow at end B. To find that, we use continuity equation, the formula number 2. A1 V1 equal A2 V2, the continuity equation which dictate that the volume rate of flow is same everywhere. So volume rate of flow at end A equal that at end B. So using this formula, we simply rearrange it and get V2 equal A1 upon A2 V1. We express area as in terms of diameter, substitute the values, and then the velocity of flow is 280 centimeter per second. The velocities above and below the wing of an aeroplane are V1, V2. A is the area. The upward force, show that upward force is given by this expression. The shape of the aeroplane wing look like this. It is called airfoil. As the plane travels with high speed, the air rushes from above and below this wing. The air flowing from above has high speed. The speed is denoted by V1, and the air flowing from below has low speed. V1 is greater than V2. So wherever there is a high speed of flow, the pressure will be smaller. Let us denote the pressure by P1. And here the speed is low, V2 is less than V1, so pressure is P2. So here we have low pressure. And here we have high pressure. Means this P2 is greater than P1 because this is the well-known Bernoulli's principle. This problem is based upon Bernoulli principle. So according to Bernoulli equation, for the air flowing from both above and below the wing, this equation holds that the sum of these three quantity is constant. P represents the pressure at a certain region, V is the velocity of flow there, and Y represent the elevation of that region from a certain horizontal reference. And the constant value is same as long as the type of fluid is same. So here we have air flowing from above and below. So for both the streams above and below, this constant value will be same. Moreover, the air is flowing horizontally. So y value, which represent the elevation from certain reference, this y value is constant for both the flow above and that below the wing. So y value is same. So because y value is constant, we can take this on here, and we already have a one constant value here, and that other constant value will be coming on this side. So we will have only constant values on the right hand side, so we can write it as a single constant. So for example, for the stream above the wing, we have this equation, Bernoulli equation for a horizontal flow. In a horizontal flow, this quantity is simply a constant, and therefore we need not consider it. So Bernoulli equation reduces to this form. Now this is a constant value, and this constant value can be adjusted to be same for both the flows above and below. We can choose different reference level for these two streams. Such reference level that the elevation with respect to that reference level is same for both the streams, one below and the other above. For example, suppose this is the reference horizontal level relative to which we measure the elevation y of different regions in the stream below. We choose another reference level little above it, and the elevation of different regions for the stream that is above the wing is y. So because the reference level is above, we can adjust this value y for the stream above to be equal to this value y, and therefore this constant value can be adjusted to be same for both the flows above and below, and then we get this equation where the constant value on the right hand side is same for both the streams above and below. This constant value is same for both the streams above and below. We write this expression for the stream above by using the suffix 1, and this is the similar expression for the stream below with the suffixes 2. These two are equal because they both are the same constant value. We have understood that the pressure above the wing is smaller than the pressure below. Means pressure below is higher. So this pressure create greater force from below the wing, and this pressure create a force that is smaller from that below the wing. So because the force below is higher, there is a net upward force on this wing. The net upward force is given by the difference between these two forces, F2 minus F1. This gives us the net upward force, which I denote by F. And it is this net upward force on the wing that generate upward lift on the plane, and the plane can fly. We have to calculate this upward lift, the difference in these two forces. The force below will be the pressure multiplied by area, and the force above is the pressure in the region above the wing multiplied by area. Area of the wing is same both below and above, so we need not care about that. So here we have an equation which contain pressure. We multiply both sides by area of the wing, and we get AP1, which is the force above the wing, and AP2, which is the force below the wing. We take F2 on the left hand side and it is subtracted, and we take this term on the right hand side which is subtracted from here. Now we have got F2 minus F1 on left hand side, which is simply the net upward force, and on the right hand side these constant factors can be taken outside common, and we have V2 square and V1 square inside the bracket, and this is just what we had to prove, the net upward force given by this expression. Next problem, water flows through the horizontal tube and it has a length of 0.20 meter. This is the horizontal tube which is attached with a vertical tube at the left hand side end, and this right end has the open end. This is the open end from which the water is flowing out. The radius of this horizontal tube is 0.081 centimeter. This is the radius. The length is 0.20 meter, which is 20 centimeter, and we have a liquid filled up to the height of 20 centimeter in the vertical tube. This liquid has a certain weight, and because of its weight, it pushes the liquid in the horizontal tube in this direction. The water flowing out from this end already faces the pressure of atmosphere, PO. We call the pressure at this open end P2. At this end in the horizontal tube, there is also a certain pressure. Already there is a pressure of atmosphere PO and additional pressure due to the weight of this liquid. Additional pressure. So the total pressure at this end is equal to atmospheric pressure plus the pressure due to the weight of this liquid in a vertical tube. So that pressure is actually the weight of the liquid divided by area of cross section upon which it acts. So area of cross section will be obtained from the radius of the tube. So we call this pressure P1. So P1 is equal to PO. The weight of the liquid is mg, mass of the liquid in the vertical tube, divided by area. Area is A. Now we can write mass as density multiplied by volume divided by A. So we write P1 here. Now volume of this liquid is the volume of the cylindrical tube, and it has the cross section area A, and the height of the cylindrical shape is h. So volume of this fluid or the liquid is equal to base area multiplied by height, and we write G as it is. We are writing this expression here and divided by area A. This area cancel. So we miss P0. P0 is also present. So P1 is equal to rho G H plus PO. So pressure at one end is P2 and the pressure at the other end is P1. So pressure difference P1 minus P2, we write here pressure difference P1 minus P2 is equal to, this is P1 and this is P2. So P0 get cancelled and we have rho GH, the pressure difference. This is the setup which correspond to Paul's law. In Paul's law, we have this setup, and Pauli derived an equation from which we can calculate the viscosity of liquid. We simply have to set the liquid in flow through this type of tube, and then measuring certain values, the pressure difference, the radius of the tube, we can calculate the viscosity of liquid. So this is the Paul's equation which is associated with this setup, and we can calculate viscosity of the liquid. Here we have a pressure difference, the pressure at one end of the horizontal tube and the pressure at the other end of the horizontal tube. And that pressure difference we have already calculated to be rho GH. So volume rate of flow is equal to this. Now we calculate viscosity eta using Paul's law. We rewrite this equation. The left hand side is the volume rate of flow, which we can write as volume divided by time. We take eta on one side and the quantities on the left hand side will be transferred towards right, and that's a simple adjustment. So here it is done. Now all the quantities on the right hand side are given in the data. We simply substitute and obtain eta in poise. Poise is the CGS unit of viscosity. We must note, before writing the unit of eta, we must note that all the units in the quantities given are in CGS system. Length must be in centimeter, time in second, weight in gram, and then only we will get coefficient of viscosity eta in poise. Next problem, this is easy problem. A capillary tube of bore 1 millimeter, that is the diameter, and has a length of 20 centimeter, is fitted horizontally to a sufficiently big vessel full of liquid of density 0.8 gram per cubic centimeter, height is 1 meter. Find the amount of liquid flowing in 5 minutes. So again this setup corresponds to Paul's law. We have a small capillary tube which is fitted horizontally, and it has the diameter of 1 millimeter, which we write as 0.1 centimeter, and it is fitted to a large tank which contain liquid of density 0.8 gram per centimeter cube. The weight of this liquid will push the liquid inside this capillary tube, and because of that push, because of the pressure, the liquid will emerge out from this other end of the capillary tube. The liquid will emerge with certain rate. and we have to find the amount of liquid that flows out in 5 minutes. So the pressure present at the open end is atmospheric pressure, and here the pressure is atmospheric pressure plus uh, the weight of this liquid. So we have already seen that if this pressure at the open end is P2, the pressure at the opposite end, which is P1, it is the atmospheric pressure plus the pressure due to the weight of the liquid. And then the pressure difference P1 minus P2 is simply rho GH, as we have seen in the previous problem. So in Poiseuille's equation, which contain the pressure difference, we replace it by rho GH. On the left hand side we write V upon T, the time is given, it is 5 minutes, we have to find the volume of the liquid flowing in 5 minutes. So we bring this time on the right hand side and we get this equation. Now we simply substitute the values of all the quantities and get the volume to be 240.5 centimeter cube that flows in 5 minutes. Water flows along a horizontal pipe of variable cross section. At a point where the velocity of flow is 30, the pressure is 1400. What is the pressure at the point where the velocity is 60? We have a horizontal pipe and it has a different variable cross section. For example, see, this is the horizontal pipe with different cross section area at different region. At one point, say here, the flow speed is 30 and the pressure P1, say this is V1 and the pressure P1 is 1400 with the unit given, and at some other region, say here the flow speed is 60, we have to calculate the pressure at this region. So this problem is about the flow speed and pressure. So we have to use Bernoulli's equation because Bernoulli's equation governs the flow of liquid at different elevation and at different pressure. So how pressure and different elevation may affect the flow speed, it is given by Bernoulli's equation, and this is the Bernoulli equation. Pipe is horizontal, that means flow is horizontal. That is y value, which is the elevation of different region relative to certain horizontal. Elevation is same everywhere because the pipe is horizontal. So y value is constant everywhere, g is already constant, density of the liquid is also constant. So this entire quantity is constant. We transfer it on the right hand side and therefore right hand side will be a constant value for all the regions in the pipe. So we are dealing with two regions in the pipe. At one region, the velocity of flow and the pressure is given. At the other region, the velocity is given but pressure is not given. So we write Bernoulli equation for the two region. For the first region, the Bernoulli equation is P1 is expressed by suffixing with 1. At the second region, we have used suffix 2 for the Bernoulli equation. We have rewritten this Bernoulli equation by transferring this constant value on the right hand side and writing it a single constant value. So this expression for one region, and this is the same expression for other region, which will be these two values will be equal because they both are the same constant value. And now we have to find pressure P2. So we transfer this quantity here and then get P2 equal to this quantity become negative on transferring on the other side. So P1 is given, V1 is given, V2 is given, and the density of the liquid is also given. Density of the liquid is water, so its density will be 1 gram per centimeter cube. So we substitute all the values and finally get pressure. Pressure is in Newton per meter square. Here we must take care. In pressure the unit of length is meter, but in velocity the unit of length is centimeter. So we must have the same unit for a given quantity everywhere. So we convert this centimeter per second into meter per second. Then everywhere we will have the unit of length to be meter, the unit of time is already second, and the Newton already involved meter for the unit of length, second for the unit of time. So we have got all the quantities in SI system, and then final value will also be in SI system. The unit will be Newton per meter square. Two tubes AC and CB of length 50 and 30 and radii 0.1 and 0.2 are joined at C. Water enters at A at the pressure of 100 centimeter of mercury and leaves at B at the pressure of 76 centimeter of mercury. Find the pressure at C. In this problem, we have two tubes of different length and different radii. A tube AC, it has the radius of 0.1 millimeter, and it has the length of 50 centimeter. And there is another tube which is wider, has the diameter of 0.2 millimeter, and its length is only 30 centimeter. And the fluid enters, this is the tube AC and this is the tube CB. C is the common point between the two tubes where they have joined. Water enters at A with the pressure of 100 centimeter of mercury. 100 centimeter of mercury, which is the height H1, height of the mercury column, which exert the pressure corresponding to its weight, and it leaves at B, and the pressure there is 76 centimeter of mercury. The pressure, when it is expressed in the height of mercury, that pressure is actually the pressure due to the weight of that particular height of the mercury placed over some surface. We have to find the pressure at C. Again, this is a Poiseuille's setup and we use Poiseuille's law. Poiseuille's setup basically consists of a horizontal tube and a vertical tube attached to it from one end. In the vertical tube, we have a liquid, and the weight of that liquid pushes the liquid in the horizontal tube. At the open end of the tube, there is a pressure of atmosphere, and at the opposite end of the horizontal tube, there is already the pressure of atmosphere from this open mouth of the vertical tube, plus the pressure due to the weight of the liquid in the vertical tube. So pressure difference is actually equal to the pressure due to the weight of this vertical column of the liquid, and the pressure due to the vertical column of the liquid is given by the density of liquid, acceleration due to gravity, and height of the liquid. So when pressure is expressed as a certain height of mercury, it means that pressure is equal to rho g multiplied by that height of mercury. So we use Poiseuille's law, which gives us the volume rate of flow, the rate of flow of liquid in terms of its volume. Now volume rate of flow must be same in both the tube because the fluid is flowing steadily. We cannot have a situation where the volume rate of flow is higher from the first tube and the flow rate is smaller in the second tube. If there is a higher flow rate from the first tube, then there will be accumulation of water at the junction. If the volume rate of flow is smaller in the first tube and higher in the second tube, means water is removed from the junction. But water is neither accumulating at the junction nor it is removed from the junction. It is just steadily flowing. Whatever the water coming to sea from the first tube, the same amount of water leaves through the second tube in a given time. So volume rate of flow is same for both the tube. So volume rate of flow is given by this Poiseuille's formula, and this formula for the first tube can be written with the suffixes 1, pressure P1 for the first tube, and radius A1 for the first tube, and for the second tube the volume rate of flow is given by using the suffix 2, the pressure P2 for the second tube and the radius A2 for the second tube. Volume rate of flow is same in both the tubes, so these two quantities will be equal. So some cancellation occur, eta and 8 get cancelled, and finally in the second step we have this equation. We have to calculate the pressure at C. The pressure at C is P. For the first tube, the pressure difference P1, P2 will be the difference in pressure at A and the pressure at C. We have denoted pressure at C by P. Pressure at A is P1 and pressure at B is P2, while the pressure at C is P. So, for the tube A, the pressure difference will be P1 minus P. And for the tube B, the pressure difference will be P minus P2, given here. We have to calculate pressure at C, means we have to calculate P. So all other quantities are given. So before we calculate, the pressures are not given directly in Newton per meter square, but they are given as some height of mercury. So when pressure is expressed as a height of mercury, we have to use this formula to calculate the pressure in SI unit, Newton per meter square. So we replace these pressures by the formula rho GH. So pressure P1 correspond to certain height of mercury. So H1 rho g, and the pressure P, it will when it is expressed as a height of mercury, we write it as H rho g, and this is the pressure P again, and this is pressure P2. P2 is the height H2 of mercury. Rho the density of mercury, and g the acceleration due to gravity will be same everywhere. Now these identical quantities will cancel from both sides. We take rho g, which is present in both the terms, we take it common, and here also rho g is taken common. They both cancel from the two sides, and we finally have an equation in terms of the height of mercury. We have to calculate pressure at C, means we have to calculate the height of the mercury corresponding to pressure at P. So we have expressed an equation, we have expressed the equation that contain P. We have expressed this equation in terms of the height of mercury by using this formula. So all the quantities are given. The radius A1 of the tube A is 0.01, radius A2 of the tube B is 0.02, and then we do some calculation. After having calculated the simple rearrangement, all these are simple algebraic rearrangement, we finally get this equation. So we have 553H equal to, we substitute for height H1 and H2 of mercury column corresponding to pressures at A and at B, and then finally get the height to be 79.75 centimeter. Now this is the height of mercury for the pressure at C. Thus the pressure at C is 79.75 centimeter of mercury. A water pipe 4 centimeter in diameter has a constriction of diameter 2 centimeter. Find the rate of discharge of water through the pipe if the velocity of the flow of water in the main pipe is 6 centimeter per second. Find the velocity of flow at the constriction. A water pipe has a constriction. Constriction means narrow region. This is the constriction. Constriction of diameter. The diameter is 2 centimeter, and the pipe has the diameter of 4 centimeter. This is the main part of the pipe where the diameter is 4 centimeter everywhere, and there is a small region where there is a constriction of diameter 2 centimeter. So velocity of water flow in the main pipe is 6 centimeter per second, which we express as, we have taken it 6 centimeter per second only, the velocity of flow. The diameter of the main pipe is 4 centimeter and diameter at constriction is 2 centimeter. We have to find volume rate of flow. So volume rate of flow is given by this formula, area of cross section and the velocity of flow. We use main pipe because we know the velocity of flow in the main pipe and also the area of cross section as the diameter of the main pipe is given. So we express area in terms of diameter as pi d1 square by 4 and substitute the values given. All values are taken in a CGS unit and we get the volume rate of flow to be 75.4 centimeter cube per second. We can express it as meter cube per second. We know that 1 centimeter is 10 raised to minus 2 meter. So 1 centimeter cube is 10 raised to minus 2 cube meter cube. That is 10 raised to minus 6 meter cube. So in converting from centimeter cube to meter cube, we simply multiply by the factor of 10 raised to minus 6 meter and we get it in a meter cube per second. Secondly, we have to find the velocity of flow at the constriction. Velocity of flow at constriction. According to continuity equation, the velocity of flow is same everywhere and the velocity of flow in the main pipe is A1 V1 and the velocity of flow at constriction is A2 V2 and volume rate of flow. So these both volume rate of flow in main pipe and at constriction, they are equal. We use this continuity equation and then find out the velocity V2 at the constriction given the areas of constriction on main pipe and the velocity of flow in the main pipe. We start with this continuity equation and then we adjust this equation to give V2. We express area in terms of diameter. Only the area A2 will have to be expressed in terms of diameter because A1 V1 is already calculated in the previous part of the problem. Here A1 V1 is the volume rate of flow. So this is A1 V1 volume rate of flow 24 pi. So we directly write it there for A1 V1. A1 V1 is written as 24 and the 4 goes into the numerator pi d2 square. The d2 diameter, the diameter of constriction is given already. It is 2 cm. It is some value that is substituted here and we get velocity V2 as 24 centimeter per second. We get velocity in 24 centimeter per second. We must take care to see that all the quantities are in CGS system. All the lengths in centimeter, all the times in second. Water flows at a steady rate through horizontal tube consisting of two tubes joined in series. One tube is 21 centimeter, another 2.25 millimeter in diameter and the other is 7 centimeter long and 0.75 centimeter in diameter. The pressure differences at the ends of the composite tube is 14 centimeter. What is the pressure difference across each part? We have a tube made up of two tubes. One tube has a length of 21 centimeter and 2.25 diameter. This is one tube. It has 2.25 diameter, millimeter diameter and has a length of 7 centimeter. Other tube is narrower and longer. It has a diameter of 0.75 centimeter and the length of 21 cent. No, other tube is shorter. It is 21 centimeter and it is 7 centimeter. The pressure difference across the ends of this composite tube, which is made up of two tubes, the two tubes are joined together. The pressure is P1 at this end and the P2 at this end. The pressure difference P1 minus P2 is given. It is 14 centimeter of mercury. So all the data is written, the lengths of the two tubes are given, the radii of the two tubes are given. We have to find the pressure difference across each tube. So suppose at the junction the pressure is P. So we have to find P1 minus P2 and P minus P2. This is again Poiseuille's law problem. So we use Poiseuille's equation. In Poiseuille's equation, the pressure difference P1 minus P2, it is the difference of pressure at the two ends of the tube in which the fluid flow is being analyzed. So we write volume rate of flow for the first tube. This is the volume rate of flow for the first tube, the Poiseuille's equation, and this is the volume rate of flow for the second tube, and the volume rate of flow is same everywhere. Whatever fluid enter, the same amount of fluid must leave in the given time. So volume rate of flow is equal for both the tube. So that's why we have equality here. We have to calculate P1 minus P and P minus P2, and we are given P1 minus P2. So some cancellation occur and we get this value, this second equation. Now we replace pressure by an expression rho gh, because when pressure is expressed as a height of mercury, the pressure in Newton per meter square or pressure as per its actual definition is given by rho gh, where h represents the height of mercury or height of any other column used for pressure measurement. So we write in place of P1, we write it rho gh1. For the pressure P2, we write rho gh2. Rho and g will remain same because the density is fixed, because we have fixed liquid mercury, and the pressure at the junction we write it as rho gh. We have to calculate P minus P1, P1 minus P and P minus P2. So let's look at the previous equation. So pressure P1 will be replaced by rho gh1, P rho gh and P2 rho gh2 to get next equation. Rho g will be taken constant on both the sides of equation and they cancel. We get this equation then. Now we take h1 minus h as x and h minus h2 as y and substitute here to get this simple equation. Now we substitute for the radii a1 and a2 and lengths l1 and l2 and do some simple calculation to finally obtain this equation. So finally we have x equal to 375y. And now the pressure difference P1 minus P2 is given. Pressure difference P1 minus P2 is 14 centimeter of Hg, and P1 minus P2 correspond to H1 minus H2. So if we take x plus y, then x plus y gives us H1 minus H2, and H1 minus H2 actually correspond to the pressure P1 minus P2. H1 minus H2 corresponds to P1 minus P2, and it is given to be 14 centimeter. 14 centimeter of mercury column. We note the equation 1 and this is the equation 2. We have equation 1 and equation 2 in two unknowns x and y. So we substitute for y as 14 minus x into equation 1. For y as 14 minus x. We substitute here in the equation 1. And then get x equal to 375 14 minus x, which we simply solve and get x equal to 13.4 centimeter. So x is equal to 13.4 centimeter. But x is simply h1 minus h, which correspond to p1 minus p, the pressure difference across first tube. So h1 minus h is 13.4 centimeter, means p1 minus p is 13.4 centimeter of water or mercury, whatever liquid is used for pressure measurement. Now having obtained the value of x, we substitute this value in equation 2 and get y, which is 0.6 centimeter. But y is h2 minus h, and h2 minus h means the pressure difference p minus p2. Actually it is h minus h2, not h2 minus h. It is h minus h2. And p minus p2 is 0.6 centimeter of water. So we stop here. Thank you.